The waves cause the basilar membrane to vibrate. In different ways depending on the sound. Fibers in the basilar membrane stimulate hair cells. Cells. Sound like from Mississippi or something. Cells that are connected to the auditory nerve. That connect the auditory nerve to the brain. I think there was a question on your quiz. Wasn't there one about the auditory nerve? To identify that. That takes the electrical signal to the brain. We're going to sort of lump the vestibule and the semicircular canals. The vestibule is right here. The semicircular canals are these things. So this is the vestibule. And then the semicircular canals. These are all fluid-filled. In fact, the whole thing is fluid-filled. But these, collectively, mainly the semicircular canals, but they help you to maintain balance. And they are fluid-filled. I want to show you a couple of things. The first video I want to show you has to do with the cochlea, and it talks about how those vibrations, which come onto the basilar membrane, where is that? It's right here, I think. The basilar membrane, that bone pushes on it, and it pushes those pressure waves into the fluid-filled chamber of the cochlea. There are particular cells within the cochlea called hair cells, and when you have a certain frequency, those hair cells will resonate with that frequency of the pressure wave. Right, so it'll make them vibrate even more. And then when those hair cells vibrate, then it sends this electrical signal to the brain. So the first thing I want to show you is just a video describing this process. And then I'll show you another one that has to do with our... For the test coming up. When is that old test? Are you serious?
Are we serious?
Wow. Better get to...
That old test.
What about it?
How about the review?
Yeah, we'll do it on Tuesday. Do you want to do it in class or outside of class? Not. I'm sorry, what?
Outside.
I'll have more time outside of class. Like if we do it in class, I'll only do about 20 minutes. If we do it outside of class, say on Wednesday afternoon. The test is on Thursday. Yeah, let's just do that. We'll do it on Wednesday afternoon. If you can't make it, I'll record it just like I do the class session. If you can't make it, you can watch the recording. I recommend if you do watch the recording, it'll be 2 or 3 o'clock. What's that? Yeah, of course. Alrighty. Or probably just put it under the class section. There's a link on the website. More about that next week. What's today? Today is Tuesday? Alright. Let's try these questions. Try the one with the ear. One up top here. All right. You'll have the same figure, by the way, on your exam for the ear. I'll ask you to identify 3 or 4 or 5 different parts. Identify them, or just tell me what purpose they serve. Let's stop at 32. Awesome, that was an easy one, right? Do not answer this question. Like it really perturbs me when y'all give the punchlines for my jokes. You understand? Are you hearing me? I forget who it is. Somebody over here does it a lot. Is it you? What do you call cheese that doesn't belong to you? Oh.
Yeah, I know that one, and I usually don't.
It wasn't a hard question anyway. I don't need to give you an original joke.
So you'll get it to
That was a good joke. That's an awesome joke.
I think you should put some jokes in the test. Yeah. See if we can get your punchline there.
Right, right. All right. From the above diagram, which fluid-filled chamber translates vibrations? All right. Let's stop at 36. 36. Awesome. D is right. The cochlea right here is the fluid-filled chamber. It's C, the sixth thing. All right, let's look at this. Which best describes the part labeled 1? So this part right here. There might be multiple possible answers, but what best describes that whole thing? I'm going to stop at 31. Very good. D is right. That's called the larynx. You might have thought that it was vocal cords or glottis, both of which are in the larynx, but it's more appropriate to call that whole sort of box the larynx that protects and helps to move your vocal cords. And then what is the function of the 3 small bones in the ear? All right, we'll stop at 20. Awesome. C is right. It transfers vibrations. These other things, this is the cochlea. To resonate, that's hair cells. And to vibrate the vocal cords, that's not really a thing in the ear at all. The Bernoulli principle is important for vibrating the vocal cords. That question could be related to Bernoulli's principle. Remember what we talked about with the vocal cords? That the muscles pull them together, you force the air through, and that separates them, and then you get that low pressure, and that causes them to collapse back down again, and then they vibrate like that over and over again. But C is the right answer to that. Hey, what do you call a boomerang that doesn't work? A stick. All right, let's look at hearing problems. Very common hearing problem is that you have an obstruction of the ear canal. Usually because you've been sticking Q-tips down in there too much. You get all the earwax compacted. No, you're not supposed to put anything in there. It's not a real doctor. Obstruction of the ear canal impedes sound. From reaching the eardrum. So, for example, you can have earwax. You can have water in there, swimmer's ear. But you know they make little alcohol drops. If you get water in your ear, you just put alcohol drops and it'll evaporate. I know.
Yeah, it's all warm.
2, you can have a perforated eardrum, where you actually get a tear or a hole in the eardrum. That can occur from sticking a Q-tip down in there too far. Or it can occur from noises that are too loud. Like a noise that's too loud, those vibrations will vibrate the eardrum too much and can cause it to rupture or tear. And then you can also have a middle ear infection, We've talked about this a little bit. I think there's a question on your quiz about it. Is that right?
Yeah.
Yeah. Middle ear infection causes fluid buildup behind the eardrum. So it just can't vibrate properly. If you've had a cold and you're all congested, right, when you get congested, that eustachian tube gets blocked and you can't drain the fluid out of your ears, and so you get fluid sort of behind your ears, and that's why it's difficult for you to hear. You just can't hear as well. Feels like you're walking around inside a box. Most hearing loss in the cochlea is due to the loss of hair cells. But you can have other problems too. This can be caused by disease, age, just old, or loud noises. You ever seen somebody with a cochlear implant? We'll talk about these later. You have? They're kind of cool. I mean, I know it's not cool for those people, but they have, their cochlea doesn't work properly. And so they have a thing that connects to their brain. It's usually on the back side of their head. Connects to their brain and actually sends an electrical signal. It takes vibration and it does the work of the cochlea where it sends an electrical signal that's based on those vibrations. We'll talk about that in just a minute. I'll show you a video. And then also you can have brain injuries or diseases that can affect hearing. Is that right? Let me see if, yeah, that comes up later.
You said that the tube's inserted in the station to drain.
Right, when you get a, I said that a long time ago. That when you're, like, when kids get tubes put into their ears, they do it to open up the eustachian tube. I don't know if it's actually put into the eustachian tube or if it's actually an extra tube. I don't know. You might know.
My eardrum collapsed. It didn't, and they said it was from having too many sets of tubes, so I guess it's like a pressure thing.
Oh, yeah. Yeah. I don't know. All right. Let's look at the intensity of sound. You will have some questions about the intensity, but as I said, I didn't put it on the quiz because I just wanted to show you how it works. Sound carries energy, like all waves. And we don't measure the energy of sound waves, however. Instead, we measure the intensity. And it's related to the energy. The intensity is equal to the power divided by the area. And remember, power, P, is equal to energy over time. And A here is area. And so the units of this, what is the unit for power? Watt, yeah. That's what I just said. Watt is the unit for power. So the units for this are watts per square meter. So if you imagine that you have this source of sound, we'll think of it as like a spherical source of sound. So it's sound that's sort of going out. Imagine you have like a spherical speaker in the middle there, and it's booming out sound in all directions. We know actually speakers are usually directional, right? They send sound only in one direction or like in a big cone. But as those sound waves go out, the intensity of the sound waves will gradually decrease. Actually, they're not gradually. They decrease a lot as you go away from the speaker. So here, the distance from the speaker to that point is our value R, and here it's a value R as well. So I have two different radii to where I have this spherical surface that surrounds my speaker. The area refers to the area of the spherical surface. Mainly, you need to understand that the area of the spherical surface is proportional to 1 over r squared. And so what that means is that as I go farther and farther away, then my intensity drops a lot. Because if I were to plot intensity versus r, it's going to look like this. It's a 1 over r squared dependence. So for example, if I move twice as far away, what happens to the intensity? It's going to decrease, but by what amount will it decrease? By a factor of what? 1/4, right? It'll be 4 times smaller. So the intensity will be 1/4 what it was originally. And that comes about from this equation that intensity is equal to P over the area, which is 4 pi r squared. That's the surface area of a sphere. You don't need to know that, but you do need to know, like you don't need to know that this is the surface area of a sphere. I'm not going to have you calculate the intensity, but you do need to know that we have this very strong dependence of the intensity on the distance from the source of sound. So if you're at a concert, you don't want to stand right up next to the speakers because it's going to be really loud. But if you just move a little bit away from them, then every little bit that you move away, the intensity is going to drop by that amount squared. If you move twice as far away, it's going to be a factor of 4 smaller. If you move 3 times as far away, a factor of 9 smaller. So the farther you move away from the source of sound, the intensity gets much, much smaller. So when you go to concerts, do y'all still go to concerts? Yep. When you go to concerts, you don't want to be right up next to the speaker, like in the fray. You want to be a little bit far away. Or wear earplugs, even better. Or wear some big earmuffs. Like that would be even cooler. It would make you look cool. Okay? You want to protect your ears, because unlike a lot of parts of the body which regenerate themselves, your hair cells, they don't regenerate. Your eardrum doesn't repair itself. So once you lose it or once you damage it, your base is not really much you can do about it. All right, there are 2 important reference points for these. These are on your equation sheet, I think. Let me double check. No, they're not. Do I ask you these? Have I ever asked threshold of pain, threshold of hearing?
No, but it's
Is it on one of your quizzes?
on one of the questions.
Okay, I guess I do then. So I like to show you this because there's a huge difference between the lowest sound that you can hear and the loudest sound that you can hear. There are many, many orders of magnitude. So the lowest sound that you can hear has an intensity of 10 to the minus 12 watts per square meter. And then the highest sound, or the loudest sound that you can hear, has an intensity of 1.0 watts per square meter. So notice there's 12 orders of magnitude. That means if I can hear this sound, it's the smallest sound that I can hear. What is this? I can also hear another sound that's, what's 10 to the 12? 1 trillion times louder in intensity. That's kind of cool, right? Just like we'll see that the same is true for our eye in a later chapter when we do light, that the eye is similarly able to detect a vast range of light, intensities of light. And that's true for your ear, too. Both of these are dependent on the person and the frequency. Yeah, although I don't like using low and high. This is quiet and loud. I did use low and high, and I'm sorry. Because we usually use low and high for, low, high. But it never gets old, does it? You're always amazed. No. Hi. Anyway, so that's our quiet or loud. These are dependent on the person and the frequency of sound to which that person is most sensitive. And remember, our frequency was 20 to 20,000 hertz. But as we found out that not everybody can hear 20 hertz, and not everybody can hear 20,000 hertz. Most of you can hear most of that range, but as you get older, or as you go to various things and your hearing is damaged irreversibly, then you come to lose some of that frequency sensitivity. Okay, looks like we have a little bit more of this, so let's just about the intensity dependence on area. If we assume the source is a point source, sorry, I jumped the gun a little bit on the area, but that's okay, we'll just cover it again. The intensity can be written, power over area, which is power over 4 pi r squared. And you don't need to know the equation for the area of a sphere, but you do need to know that it's dependent upon the radius squared. That's generally always true, right? When we're talking about the area of something, that is dependent upon some length measurement squared, which in this case is the radius. Here, r is the radius of the sphere. And what happens to I as r increases? I will drop. But it's not a linear relationship, it's a quadratic relationship, so it drops a lot. I drew this graph before, but let me draw it again. It's going to drop a lot. If r triples, if r goes to, say, 3r, for example, then I will go to 1/9 the original intensity. Or if r quadruples, I will go to what? If you move 4 times as far away, what's going to happen to your intensity? 1/16. All right, 1 over 16. Or if I double r, I have a quarter of the original intensity. And we've seen this mathematical relationship. It's called the inverse square law. In fact, we've seen the inverse square law a lot, that we have this 1 over r squared dependence, and it's because we have spherical symmetry in nature, that we have a lot of different things, the gravitational force, the electrical force, the intensity of sound and how we measure it, a lot of different things that are dependent upon their spherical symmetry. And that's why we have this mathematical relationship wherein I is proportional to the inverse of the square of r. Okay? So it implies that the sound is emitted in all directions. And so like if you're at a football game and the cheerleader has one of those megaphones screaming into your ear, like you have to move farther away in order to get the intensity to drop, because that sound is more channeled towards you. Okay, let's look at sound intensity level. I know that in the book that it probably sort of confused you, but there are really only a couple of things that I want you to be able to do. And once you see those couple of things, you'll say, gosh, that's really easy. Decibels, I mean, in measuring sound intensity and sound intensity level. If the intensity of a sound is 10 times that of another sound, then a person only perceives it to be about twice as loud. That's important because remember, threshold of hearing to threshold of pain is a factor of 1 trillion, from 10 to the minus 12 to 1. And so in order for us to be able to discern between such a vast range of volumes of sound, then our ear can't pick up on every little subtle change in sound. So if I increase the intensity of a sound by a factor of 10, then I'm only going to say, oh, that sounds about twice as loud. If I'm presented with several noises that have different intensities, a factor of 10 is going to perceive to be about twice as loud. And because of this difference, this sort of how our perception is a lot smaller than the actual change in intensity, we use a different kind of scale, a logarithmic scale. To measure loudness, and this scale measures the sound intensity level. So we have sound intensity, that's the power over area, and now we're dealing with something different called the sound intensity level. It's a different quantity, even though it sounds a lot the same. And the level is given by this equation, which you're not going to have to use, but I'm going to write it for you anyway, because you might see it. Some of you might go on and, I don't know, were there any auditory folks in this class? I don't think there are. No? Anyways, you might see it elsewhere as you move about. But L, the sound intensity level, is equal to 10 times the log of I over I naught. And here I naught is the threshold for hearing. Remember, the threshold for pain was 1 watt per square meter. This is 10 to the minus 12 watts per square meter. And this is measured in decibels. Or commonly, we see it as dB. It's really one of the few places that we use this metric prefix. Learn your metric prefixes. We never said the metric prefix deci, because it's a metric prefix that means 1/10. But for whatever reason, I forget the history behind it. But the actual unit is bells. But instead of using bells, we use decibels. And so we have this metric prefix. And that's why, by the way, in this equation, we have this factor of 10 to take that unit and convert it into something that's a tenth of what it should be, or a tenth of the bell. So the unit is actually the bells, but we're just going to call it the decibels. So if your friends ever ask you, why do we have to learn that deci metric prefix anyway, which you didn't have to in this class, but why do we have to learn that? And you tell them, well, it's important for the decibels, because it's a metric prefix. Did you know that? That was a metric prefix? You did? Yeah. All right. The intensity of two sounds can be compared, and this is one thing that you'll have to do. Where I1 over I2 is going to be equal to 10 times delta L. That's our sound intensity level, or our change in sound intensity level, divided by 10. So what this means is that if I have a change in 10 decibels, that's going to result in a sound that is 10 times as intense. So I would have I1 over I2 is equal to 10, and then my delta L, which will be equal to 10 decibels, would be right here, divided by 10. So that's 10 to the first power, which is 10, and that's where that 10 comes from. So if I go from 40 decibels to 50 decibels, for example, that's an increase in 10 decibels, going from 40 to 50. That means that my sound is going to be 10 times as intense. The intensity will be 10 times what it was. I've added 10 decibels, but my intensity is multiplied by a factor of 10. I'll show you some examples. Once you see it, it's easy. So for example, 30 decibels is 10 times as intense as 20 decibels, right? Because that's a delta L of equal to 30 minus 20 equals to 10. So my intensities, my ratio of my intensities is equal to the 10 to the 10 over 10. That's just like we did before, right? However, let's say if I have 50 and 30. In this case, my delta L is 50 minus 30. What is that? Minus 20. And then the ratio of my intensities will be equal to 10 to the 20 divided by 10, or 10 squared. So if I have an increase of 20 decibels, then that means that my sound is how many times as intense? 100 times as intense. Or if I have, say 50 and 20 here, what would that be? How much more intense would that sound be? 1,000. So really what I want you to know are these decibels. I want you to be able to determine what is the difference in the intensities. What is the ratio of the intensities? How much louder is one sound to another based on an increase in the number of decibels? And they'll be simple numbers like these. They'll be factors of 10. It makes it a lot easier. So if I increase my decibels by 10, then that's an increased intensity by a factor of 10. If I increase by 20, that's an increase in intensity by a factor of what? 100. Right. If I increase by 30 decibels, that's an increase in intensity by a factor of 1,000. 40 decibels, 10,000. 50 decibels, a factor of 100,000, and on and on. It's a logarithmic scale, not a linear scale. And that's how a logarithmic scale works. You may have not ever seen a logarithmic scale, have you? Seen a logarithmic scale? Yeah, you might have seen one. They're useful for looking at things that change a lot over long spans. And that's the way the human ear works, that it changes, it detects a very large range of sound. Tests. Need to be able to do that for the test. Look back at those old questions. I know a number of you were confused about them prior to the quiz, but make sure that you can do those. You'll have one or two questions like that. I mean, everything's on the test, but people tend to have problems with this. All right, I think we'll have a question about this soon. Earplugs. They block sounds from entering the ear canal. Sound waves from entering the ear canal. They can be pretty effective. They can block out, if they're put in properly, they can block out basically all the noise. Most people, when they put them in, they don't really put them in correctly. Like they're sort of sticking out, flopping around. But to really put in a good pair of earplugs, first you got to twist them up so they're really small, and then you got to hold your ear to get your ear canal straight. Is it up or down? You put it down, and then you put it in there, and then it expands, and then basically you can't hear anything at all. Does anybody have earplugs in right now? No? Okay, good. When we go camping, especially if we go to Tickfaw, because something about Tickfaw, it's like there's college students there a lot, and they just stay up late talking and hanging out and stuff, and they're kind of loud, and they play music. And so whenever we go there, I'll put in my earplugs. We go to bed like old people. We go to bed like 8 o'clock. But we'll put earplugs in my ears, and I can't hear anything. It's like completely, all of the sound is completely muted. But anyway, they're rated by the noise reduction rating. They're given this noise reduction rating, or the NRR. The NRR is in decibels. So, for example, a rating of 20 dB should decrease the intensity by a factor of what? 100, right. So, by a factor of 100. And the way I do that, what I think when I'm thinking of this, I think, oh, I have 20, and then I just get rid of the 0, and I put it 10 to that power. 20 is the difference in the 2 decibels. By how much my decibels being decreased, I get rid of the 0, make it 20 divided by 10, and then it's 10 squared, which is equal to 100. Another means of sound reduction involves interference, sound waves, or interference of waves. We've seen this. Remember that video that I made y'all watch with the seal? Like the really arrogant and mean seal that got what it deserved from the killer whales? Did I just say that out loud? I was thinking it. No, the cute little seal that got eaten by the killer whale. Remember what the whales did? Is they took waves and they added them up to make a much bigger wave, right? You can do that. But something else that you can do is that you can take waves that are out, we call these out of phase waves. If I add these up, they're going to make a wave with nothing. And actually, if you're clever and you sit for a long time and you watch water waves out on a lake, when you have two boats that are coming in, sometimes you'll see those waves come together, the wake of boats, and they'll make bigger waves. But sometimes you'll see waves coming in from two boats, like as they meet out in the surface of the water, and you'll see still portions of the water. And that's where you're actually getting an interference of waves that produces this, which has no energy remaining, as opposed to this, which makes waves with higher peaks and crests, or higher peaks and troughs. And so something that uses that principle of interference are noise-canceling headphones. Who has noise-canceling headphones? Anybody? They're usually pretty pricey. I don't have them. You have some?
My roommate does.
Yeah, they're pretty nice.
$300.
Yeah, yeah. So noise-canceling headphones, what they do is they detect the ambient noise, and they produce an out-of-phase sound wave. That's what we call, by the way, this sound wave. It's out of phase. It's been shifted over so that the peaks and the troughs now line up with one another to cancel the outside sounds. So for example, you know, the dog barking, the roommate talking, all that, it might have a form that sort of looks funky, maybe sort of like this. And then your wave, your noise canceling headphones will come along and they'll make something that looks like that. And when you put these two waves together, this is the noise, this is the extra sound that the headphones actually produce and put it into your ear. In your ear, these two waves will combine, they'll add up, and they'll leave nothing at all. And so that's what it means to have noise-canceling headphones. Oh goodness, it's time to leave already. Y'all have a great day. I'll see you on Thursday. And be preparing for that test coming up on Tuesday or Thursday? Thursday. Be preparing for that test. Okay, right now is when you need to be studying. Have a great day.